Greetings everyone. Welcome to Side A, Side B. In this video, we're going to be doing more background work to solve another divisibility problem. We're going to see if the following equation holds. The difference of C sub I equals C sub 0 plus sigma C sub n minus sigma C sub n minus 1. So what's in our toolbox? To start, refers to the following. Quote, my method is subtraction. I use erasers to make the images in my paintings. You really have to see it to fully get it. But it is basically erasing shapes from a background of paint. Unquote. By Artist Floyd Cooper. Can that really be the case? Erasing negative or positive space to get results? We're going to see if it applies to maths as well. Because strangely enough, that sums up the method to learn more about the composition of sequences and series. As it were, the Cooper method. Let's begin. Welcome back. In this video, it's going to be more background knowledge to help us solve a problem. And we're going to be introducing that problem shortly. The problem is still in the topic of divisibility. In this video, we're going to be looking more closely at the delta difference operator. And that should help us, give us a better understanding of the composition of sequences and series. So suppose A, B, and K is in the element of integers and M is in the element of positive integers, such that A sub I equals A sub 0 plus Km and B sub I equals B sub 0 plus Km. There's some construction next door, so the ambient noise is going to be a little bit different than usual. So if their remainders do not equal each other, then A mod M can't equal B mod M. So let's do a proof. Just consider two arithmetic series, C sub 0 plus C sub 1 plus C sub 2 C sub n minus 1 plus C sub n, and a similar series just named D for some integer n. Then the following equation holds for all n. That's our claim, which is C sub I equals C sub 0 plus sigma sum notation C sub n minus sigma C sub n minus 1, which equals C sub 0 plus C sub n. And we've done a proof of the general formula for an arithmetic series, so we can refer to that. So we're good to go on that. So consider the following equation. C sub 0 plus C sub n plus C sub n minus 1 C sub 2 plus C sub 1 plus 0 minus that expression, except for the term c sub n, which equals cn plus c sub n plus c sub n minus 1 dot 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 plus c sub 2 plus c sub 1 plus 0 minus c times n take away 1 plus that expression except for the c sub n term. All right, and if you notice, there's an nth and n minus 1 nth constant c derived from the sums, respectively, which gives cn minus cn plus c plus those two expressions. To save some space, should be clear on what those two expressions are. And then, after simplifying, cn minus cn just goes to 0, and then we have c sub 0 plus cn plus c sub n minus 1 plus dot 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 c sub 2 plus c sub 1 plus 0 minus the same expression except for the c sub n term. And notice all of the terms cancel except for the c sub n term, which gives c sub 0 plus c sub n equals c sub I. Now, if you saw the first video, that shouldn't be much of a surprise because of the delta difference operator. Now, obviously, delta can mean change. In this case, delta symbolizes finding the difference. Nice. But we're not quite done. So let's rub off the blackboard. So that wasn't much of a surprise. If we have, like in our first demo, if we have two similar series, and then if we find the difference of them, and if one series has one more term than the other, then finding the difference just equals that one term. All right, so carry on with the proof. Hence, the same must hold for d sub I. Then, let's assume c sub I equals d sub I, asterisk. And we're just labeling that equation with an asterisk. So let's find c sub I minus d sub I. And if they equal each other, then their difference should equal 0. Given that Jn equals Jn, it follows c sub 0 plus c sub n minus d sub 0 plus d sub n equals c sub 0 minus d sub 0 plus c sub n minus d sub n, which gives c sub 0 plus c sub n minus d sub 0 plus d sub n equals c sub 0 minus d sub 0. Now just consider Jn equals Jn, which means the terms c sub n and d sub n are equal. So if we find the difference of them, it just goes to 0. If we take mod n of the remaining 6 terms, we get the following equation, and then all the n terms get canceled, which just leaves c sub 0 mod n minus d sub 0 mod n equals c sub 0, well, it's just the same term, just the same expression, but it shows c sub I can't equal d sub I for any j. So our assumption is false. So the equation with the asterisk holds only if c sub 0 mod n equals c sub 0 mod n. In other words, that equation holds only if the remainders are the same. Therefore, if it holds for some integers c, d, and j, then it holds for integers a, b, and k. Therefore, for any arithmetic equations, a sub I equals a sub 0 plus mk, and b sub I equals b sub 0 plus mk, if their remainders do not equal each other, then a mod m can't equal b mod m. End of proof. Well, we found the difference of them. Let's see what happens if we sum them. So it shows that only the remainders can transform an equation. We can transform the equation if we change the mod, but if the mod stays the same, only the remainders can transform to arithmetic sequences. So let's add them. Let's sum them in order to learn more about the composition of sequences and series. So that being said, we know s sub I equals s sub 0 plus s sub n, which equals c sub 0 plus c sub n plus d sub 0 plus d sub n, which equals c sub I plus d sub I. Now we're assuming that summing those equations equals s sub I. So if that's the case, if we find the difference of s sub I, summing the differences of c sub I plus d sub I should equal the difference of s sub I. That was in words. In symbols, s sub 0 plus the sigma notation, s sub n plus 1 minus sigma s sub n, which equals c sub 0 plus d sub 0 plus sigma c sub n plus 1 plus sigma d sub n plus 1 minus sigma c sub n plus sigma d sub n, which simplifies to c sub 0 plus sigma c sub n plus 1 minus sigma c sub n plus d sub 0 plus sigma d sub n plus 1 minus sigma d sub n, which just equals c sub 0 plus the difference of c sub n plus d sub 0 plus the difference of d sub n, which equals the difference of c sub I plus the difference of d sub I, and that equals the difference of s sub I. And that's going to tell us a lot about the composition of a series as we go further. So let's do an example. using that same equation. S sub I equals C sub I plus D sub I, which equals n plus 1 cubed equals n cubed plus 3 times n squared plus 3n plus 1. Then let's find the difference of S sub I equals the difference of C sub I plus the difference of D sub I. How's that going to look in an example? Well, the difference of S sub I is one term more than that series. So n plus 2 cubed minus n plus 1 cubed. That's the difference of S sub I. And the difference of C sub I plus the difference of D sub I equals n plus 1 cubed plus 3 times n plus 1 squared plus 3 times n plus 1 plus 1. Take away n cubed plus 3n squared plus 3n plus 1. We just grouped the terms in the same way we did in the beginning. Rearranging the terms gives us the following expression on the right-hand side. And generally speaking, notice that there are some. The whole expression is actually a sum. Well, the difference of C sub I plus the difference of D sub I, the following expression. And that checks. Save a little bit of time. That's a lot of algebra doing, canceling and finding all the like terms, but you can check for yourself. When we do all the canceling and gathering all the like terms, the expression goes to, the right side of the equation goes to 3 times n squared plus 9n plus 7. So what do you think? How was the unofficial Cooper method to understand the composition of sequences and series? A starting point to help us understand the composition of polynomials in general. Whatever the result was, it's been a pleasure to make this video for you. See you in the next one.